Now you may have seen this analytical definition of limit uh, of a sequence, or the limit at infinity, that is limit of this quantity an as n goes to infinity is L. That happens if for any given epsilon greater than 0 we can find an n such that if we take our index here bigger than this big N, then an minus L, the absolute value, that is the distance of an from L, will be less than epsilon. That is, we can bring an as close to L as we please. That is, that is, we can take this epsilon to be as small as we please by taking this index n sufficiently large, and that is what this stands for. So as an example, let's look at this here. Or let's just take a couple of examples real quick. So for instance, say we got an equals n to the power 3, okay, divided by 2 n to the power 3, and say plus 5. Okay. Now here, even from pre-calculus, that as n goes to infinity, the limit is how much? 1 over 2 here, okay? Or you can use L'Hopital on the continuous version of this, or continuous transformation, or continuous description of this. So say we want to do this, say we are taking epsilon to be, okay, let me take a value that looks closer to epsilon, okay. Let's take epsilon to be 0.0001, okay. Then what we want to do is this, would like an n such that this happens, right? This portion here, that is sorry about that, okay, such that an, that is this, minus L, that is 1/2, okay, that's less than how much? 0.00001, okay. All right. In fact, I'm just going too fast here. Little n greater than or equal to n, that implies that the distance between this and 1/2 is less than 0.00001. So let's go and work on it. That is, say we got this here, okay. So this means what? That if we take common denominator, that is, if we take, let's take common denominator here, what the common denominator will be, and actually that will be the lowest common denominator as well. That is 2 times, and we got this here, times this, and then we have 2n cubed, okay, minus 2n cubed again, sorry about that, minus 2n cubed, okay, and then minus 5, okay. That has to be less than this quantity. So if this happens, or if we have the 2n cubed and 2n cubed will cancel, so we are left with only this, all right. And this will be dropped if we take absolute values, so we will just go ahead and write it as 5 over 2 times this, that's less than 0.00001, or in other words, we may do this, say we just go ahead and flip this quantity. So we have 2 times this quantity over 5, and if we reverse it, the inequality will reverse. That is, we got 1 over 0.00001, okay, and then 1.0001 is 100,000 here. So what we get is, if this quantity is greater than 100,000, okay, or in other words, if I just took it, this example, so I'm completing it here, okay, so that is if this quantity, we can just multiply both the sides by 5, and the inequality remains the same because we are multiplying by a positive number, and that means or if, okay, we have that this quantity is greater than, we can divide 500,000 by 2, right, which will become what, 250,000. So this 2 is out, okay, and then what you have is, or if, okay, even though it's not going to matter much, but 2n cube greater than, sorry, so greater than, let's subtract 5 from here, okay, that is, or if 2n, sorry, 2n cube is greater than, let's just perform the subtraction, so we get this, and this is equivalent to saying that n cube is greater than this quantity right here, this divided by 2, okay, or n is greater than, n is greater than how much? The 5th root of this quantity, okay, so let's look at this here. So this is the 5th root of this, and you can use your calculator now to get an approximate value, okay, so here is an approximate value. What is it? Sorry, not like this, but so what happens is that in this case, just capital N equals 11 will suffice. That is, what was the limit? 1/2. So if I just took capital N equals 11, so say I took it as, let's take it as 11 times that, see how much it is or how close it is to 1/2. So this quantity is how much? Actually, it's not less than 0.00001. So I must have made a mistake somewhere. Okay, and here it is. See this? Instead of 1 over 3, I took the 5th root. Okay, so let's see, it will be a little more. It's like 49.99. So we need 50 terms. So here, if I put, so that's why it was a mistake. So if I put 50 here, okay, and 50 here, and let's just subtract 1/2 here so that I don't have to apply my tired head anymore, okay, and this is, well, we had to have absolute value less than that, and you can see this here. If you took the absolute value of this quantity, okay, that will definitely be less than how much? less than 1, or let's just look at this here. So we got this times 10 to the 6, no, sorry, negative 6, okay? And that is what it's in scientific notation. So 1, 2, 3, 4, 5, and then 9, 9, 9, 9. How many nines? 4 nines, 8. And that is less than 0.0001. So here just 50 terms were enough, and you know this, that if we had n to the power 5 over here, then just 11 terms were going to be enough. But situation may not be always like that fast, so let's just take one more example. So say for instance a sub n is equal to, let me take something like 2 to the power 1 over n. Now in this case, as n goes to infinity, you can see 1 over n goes to 0. So 2 to the power 0 is how much? That's 1. So limit as n goes to infinity, okay, of 2 to the power 1 over n, that will equal how much? Let's just put this down here. No shortage of space. That has to be 1. So now say we have to find this, to find n such that if we took our little n greater than or equal to big N, then what should happen is this: 2 to the 1 over n minus 1. Say we want that to be less than 0.00001, okay, as in the last case. Now you know this, that no matter which power on which root of 2 we take, it has to be greater than 1. So we can replace this absolute value, and that is less than 0.0001. That's what we need, okay? Or in other words, what we want is we can move n to the other side. Sorry, 1 to the other side, I meant. Okay. So here we go. So if I add 1 here, we get this. And now we have to find a value on n. So it's a good idea to take natural log, or any log you can take. Natural log is good, and natural log is monotonic. So we will get this statement. All right. So you have this statement now, and we can just keep on saying our connective, like or, if, at every step. So once we go like this, what we got here is that 1 over n ln of 2 has to be less than 0.0001. Now we want a statement in n, so what we can do again is just reverse the inequality. So what we will have is that n, okay, so if we reverse the inequality, then we would have just n over, oh, I forgot my sign of ln here, okay, 1.001. So we have this divided by ln 2, okay, that's greater than how much? 1 over ln of 1.001, okay, because here we just reversed it. I don't know why I didn't write that in simpler form, okay, because I know you don't need me to explain this, but I'm doing that to just avoid me making any mistakes. So this is if n is greater than how much? ln2 over this guy ln2. Okay. And this is going to be what? So this is about 69,315. So our n in this case has to be this large. And of course, you can see we have experienced it in this discussion series enough. That is, it may even be much larger than this. So let's just go ahead and calculate if we have gotten it sufficiently close. That is, just take this power and see if it is less than 0.0001, and I think it is, right? Because we get 5 zeros, then 9, so that will be less than that. And let's see, say we take less in this case, what will happen? Okay, that is, say we took this, then it is going to be, well, it's going to be slightly more than 0.00001. Okay, so this one is the smallest such big N. All right,